Hi, I'm Sivakumar. In this video, I'm going to explain different kinds of verification methodologies that we use to verify the RTL design. You think of design. To create a perfect synthesizable model, you really need to understand the RTL design methodology. RTL means Register Transfer Level Design. Similarly, to create a complex software program, you need to understand the software design methodology like object-oriented programming. Same way, to write test benches in system Verilog, you need to understand the verification methodology like constraint random coverage driven verification. That's what I'm going to explain in this video. I'm going to explain the concept of constraint random coverage driven verification. All right. This is our proprietary data. Please read this confidential note. Look at this agenda. This is how I planned this module. Initially, I will explain why we verify every transformation step in the design flow. Also, I will explain the concept of functional verification. Then I will walk you through the verification process. Then we will discuss about the concept of reusable test bench, how we implement test benches in system Verilog, and how system Verilog test bench is different from Verilog test benches. Then we will discuss about test bench architecture. Also, we will look at the difference between directed and random test cases. That's what really needed for you to understand constraint random coverage driven verification. Simply speaking, CDV, coverage driven verification. Finally, I will brief about different kinds of methodologies that we use to verify RTL. All right. Why do we verify every transformation step in the design flow? Look at this design flow. If you consider the transformation specification to GDS2, it's a huge transformation. In reality, it doesn't happen like this. So it goes through various steps. Like from spec, we create the architecture, and based on the architecture, we write the RTL. Then we synthesize the RTL and generate the netlist. And then we take the netlist through P&R. Finally, we produce GDS2. And then GDS2 goes to foundry. Foundry fabricates the chip. And then using the chip, we create the PCB. And that's how basically we realize the product. Now, if you consider the design flow, we verify every transformation step. Let me explain how we do this. Specification. Specification is nothing but a document. It explains everything about the design. Then based on the functionality, experienced engineers like me, architects, they create the architecture. Then the question is how we verify the architecture. To verify the architecture, we create behavioral model. Look at the process. We have created the architecture from the specification, and based on the architecture, we create functional model. It's also called as transaction level model. Why we call this as TLM? If you look at this functional model, the input is transaction, the output is also transaction, and everything is going to happen in terms of transactions. So the input will be packet, output will also be packet, and within functional model, everything will happen in terms of packets. That's why it's called as transaction level model. When it comes to verifying the architecture, we look at certain things like verifying the functionality and performance. So we don't focus on implementing the hierarchy, the structure. The focus will be more on functionality and performance. So what is really needed for TLM is the speed, simulation performance. If you look at the RTL, basically it's a structural model. So obviously the simulator is going to take much time to process the information. The simulation will always be slow on RTL. But if you look at functional model, it's faster than RTL. So it helps us to run even software also on the model and check how the whole system is going to behave. So we can even use the software itself as stimulus to verify the functional model. And this is called hardware-software co-verification. That's why simulation performance is critical. If the simulation is going to be very slow like RTL simulation, then we won't be able to run software on functional model. Usually we use languages like System C, C++ to create this functional model. Now we have the powerful language System Verilog, so we can also use System Verilog to create this kind of functional model. This is a huge advantage. If you are working as a verification engineer, you have been using System Verilog for writing test benches and you are very comfortable with System Verilog. You can also implement functional model in System Verilog. All right. Look at the RTL. RTL is nothing but register transfer level design. This is the methodology we use to write synthesizable model. Basically, this is hierarchical structural unit. We realize the design in terms of various modules. It's synthesizable one. When it comes to synthesizable model, the focus will be more on area and clock frequency. This is the difference between TLM and RTL. In case of TLM, the focus will be on functionality and performance. In case of RTL, the focus will be on area and clock frequency, and eventually the model should be synthesizable. That's how we are going to generate the netlist. Usually we use HDLs to create synthesizable model, languages like Verilog and VHDL. But for TLM, we always use higher level languages like System C and System Verilog. All right. During verification, how we use TLM. If you look at the test bench, we create a component called scoreboard. Scoreboard is the component which compares the output data with reference data. During simulation, we use this TLM to produce the expected values. So we are going to instantiate this TLM as part of our System Verilog test bench. This is going to be the golden reference for DUT. And when we generate stimulus, look at this input side. The stimulus will be given to both TLM and RTL. The TLM is going to produce the expected value and the RTL is going to produce the exact output, and the scoreboard is going to compare the DUT output with expected values. That's how the scoreboard is going to compare the values and generate the message whether the test case passed or failed. This is how we do verification. So here I want you to understand how we verify the design architecture with the help of TLM, and then later on how we use the same TLM to verify even the RTL. All right. So we use transaction level model to verify the design architecture. We created the design architecture. Now we want to understand whether the functionality has been implemented in design architecture. For that, we have created transaction level model and we have run simulation on the model and we check whether we are getting the same functionality. Right, the architecture has been verified. Now the next step is RTL. So based on the architecture, the designers are going to write the RTL code, register transfer level code, and we verification engineers are going to verify the RTL. So to write RTL, obviously we need to write test bench. So test bench is the component which generates stimulus. The stimulus will be given to the DUT. When the DUT produces output, the test bench is going to collect the output and compare the output with expected values. That's how the test bench is going to verify the design. To run simulation, we need to come up with a detailed verification plan. If we are going to deal with different things like block level verification or subsystem level verification or chip level verification, then we need to identify the right verification methodology. For block level verification, we prefer white box verification. When it comes to chip level verification, we prefer black box verification. But when it comes to subsystem, we go with gray box verification. Gray box is nothing but the combination of white box and black box. And during simulation, we generate different kinds of coverage information. So how we are going to merge all the coverage information and generate the final report, and how we are going to sign off the verification, that's nothing but coverage closure. In addition to the verification process, you also need to understand the test bench architecture, which is very critical. If you really want to implement a reusable test bench, when I say reusable test bench, we need to think how we can use the test bench across different projects or across different levels of the design, like from IP to subsystem, subsystem to system level verification. So that's where the architecture becomes critical. And you also need to understand how to deal with coverage information and sign off the verification. This is how the simulation environment would look like. You will be writing the source code, you will be generating coverage, you will be looking at the waveform, you will be looking at the output messages. So there will be different things as part of the simulation environment. We have run the simulation. If there are any bugs, we need to fix the bugs in the RTL design. Then we need to rerun the simulation. It's going to be iterative process. And once we are done with simulation, we are the people, verification engineers, going to sign off the simulation. Once we approve the design for synthesis, then it goes through synthesis. And during synthesis, we convert the RTL into gate level netlist. Now, we also need to verify the netlist. This is something very important you need to understand. Synthesizer itself is a software. So we are not sure whether it converted the RTL code properly into netlist. Are there any bugs in tool? So we need to compare the netlist with RTL design. How we do that? There is a methodology called equivalence checking. This is RTL. From RTL, we have generated gate level netlist. Now what we do is we use a tool called equivalence checker. So we feed both RTL and netlist to the tool. The tool is going to compare netlist with RTL design, and if it is going to find any mismatch, it's going to report as error message. So it might convert the RTL into mathematical equations like minterms or max terms, and netlist into minterms or max terms, and eventually it might compare every minterm with minterm or max term with max term, and if it is going to find any mismatch, it's going to report error. That's how equivalence checking works. You don't have the option of doing equivalence checking, then you might want to run simulation. So whatever the test bench you have created for RTL, you can think of using the same test bench even to run simulation on netlist. So whatever the waveforms you are going to get, basically you are going to compare the waveforms with RTL waveforms. That's how you are going to verify the functionality of the netlist. All right. We are done with equivalence checking. It's verified. Now the netlist is ready. Then before moving further for P and R, what we do is basically we insert DFT logic, design for test logic. Let's look at this. Scan flip-flops. Scan flip-flops will have multiplexers at the input. Let's look at the design structure. So what we do is, in RTL, we replace the usual flip-flops by scan flip-flops. So every flip-flop is going to have multiplexer at the input, something like this. Then I can think of running the design on different modes like normal mode and scan mode. During normal mode, the data flow happens like this. So with the help of multiplexer, we put the design on normal mode. So you can choose either mode like normal mode or test mode. So during normal mode, the data flow happens like this: register, then combinational logic, then register. But during test mode, what happens is it connects all the flip-flops like scan chain, something like shift register. So we would be able to pump in the stream of bits through all the flip-flops, whether we are going to get the same stream of bits through output flip-flop. So we are going to inject the stream of bits through this flip-flop, and all the bits will flow through all the flip-flops, and eventually we should be able to get the same stream of bits through output flip-flop. If it works fine, then we would be able to confirm all the flip-flops work fine. So this will be useful to identify the fabrication faults later. This is called design for test logic, right? And we take the netlist through P and R. If you look at the front-end design flow, basically we verify the functionality of the design. We have the specification. From the specification, basically we create the RTL. Then the important question is whether the RTL works as per the specification. So we need to verify the functionality of the RTL design. That's what we do in front end. But when it comes to back end flow, we verify the timing. So after P and R, the layout will be ready, and we look at whether the design meets the timing requirements. That's where we apply static timing analysis methodology. For every flip-flop, we may need to follow setup time and hold time. Are there any setup time violations? Are there any hold time violations? If there is any violation with respect to setup time and hold time, eventually the design will get into metastable state. So in order to avoid metastable state, basically we need to take care of setup time and hold time. And we use static timing analysis to verify such timing violations. There are two ways. You can run timing simulation and check whether there are any timing violations, but that's going to be very slow because you are going to run simulation on netlist. If you look at the RTL itself is a structural unit which is going to be slow during simulation, but you have converted RTL into netlist further. Now the entire RTL is going to be in terms of gates. So that's going to be still very slow. So nobody prefers simulation for timing verification. Mostly we go for static timing analysis. So there are tools available, EDA tools available. Once we feed in the routed netlist based on SDF file, the tool will be able to analyze the entire netlist and it would be able to report all kinds of timing violations. That's how it works. We don't really need to write any test bench. We don't really need to run any simulation. Simulation is very slow. This is called static timing analysis. All right. We are done with timing analysis, no timing violations. Then we take the netlist through layout implementation. So after implementing the layout, we take the netlist through physical verification. One is design rule check, DRC. That's where we check whether we follow the design rule for the fabrication. For a particular technology, based on lambda, we have to define the width of metals, we have to define the space between the metals. All those things will be verified as part of design rule checking. Also, we do layout versus schematic verification. That's also part of physical verification. So in this case, whatever the layout we have created, the final netlist GDS2 will be compared with the reference netlist, which is nothing but the netlist generated from synthesis. So here the question is, are we retaining the functionality as part of the layout also? Maybe during P and R, if we change the structure of the design, whether it has affected the design functionality. So this is where we do equivalence checking again. In this case, the GDS2 will be compared with the original netlist. This is called a layout versus schematic verification. Finally, we get the verified GDS2. The GDS2 goes to foundry. Foundry fabricates the chip. Once we get the chip, then we take the chip through testing. This is where we inject the stream of bits and we check whether there are any fabrication faults within chip. There could be different faults like stuck at 0, stuck at 1. There could be short circuits, there could be open connections. That's where we check how the chip has been fabricated. Once we confirm that there are no fabrication faults, then we use the chip and create the final PCB. And we run software on the PCB and check whether the entire system works fine. This is called board level validation. This is how we verify every transformation step in the design flow. All right.